and that one times the base of this trapezoid is just going to give you the area. So you add up all of these areas and you multiply by G, and then you're going to get the vertical stress. Make sure that your units are consistent, okay? I'm not going to talk a lot about units here, but if you check in my notes online, there you will find an explanation about the units, about how to use PSI, how to use megapascals, pounds per gallon, anything. But basically, this is the operation that you have to do. It's basically adding up the weight of each layer. Do you see that this is density, this is gravity, and this is the thickness? So in order to calculate the total vertical stress, you just need to add up the weight of each layer. And that's it. That's everything you have to do. Okay, so that's all that you have to do in order to calculate SV. Here, SV. It's relatively easy, I would say very easy compared to the other ones that we're going to have to compute. And this is the stress in which we're going to have the highest certainty about what the value is, because it's just weight. The errors in the density tool are going to be very small compared to other errors in determining pore pressure, determining horizontal stresses. This is going to be always your best friend in geomechanics. This is the parameter in which you have the highest certainty. And this is the first one that you have to calculate before you do anything. And the way to calculate it is just this. It's as easy as that. When you have water, it gets a little bit different, but you just need to consider that the bulk density, in this case, is just the density of water, and it works exactly the same. And of course, it's a lot easier when the density is constant, and when the density is a constant, the equation simply becomes density times G times depth. Do you guys know what is the typical gradient for total vertical stress?
1 PSI per foot.
Yes, that's a typical gradient. So this thing is called the vertical stress gradient, and it is typically one PSI per foot or 23 megapascals per kilometer. And I think that's what we used last time in order to tell what was the depth at this location. So if we know the gradient and we know what is the maximum value or the value of vertical stress, we can tell what is the depth, right? In this case, what we use is just SV is the average bulk density times G times depth, in which this value is 1 PSI per foot. If you want to be a little bit more accurate, another thing you could do, you could actually calculate the gradient from here. Because you know the values, absolute values of vertical stress, and you know also from the data, it's something in the paper, that the grid spacing in vertical direction is 25 meters. So every grid here is 25 meters, which means that this is going to be from here to there, it's 200 meters. So if you know the variation of depth and you know the values of vertical stress, you can also calculate what is the actual stress gradient, which is going to be the difference between this value and that value divided the distance between here and there. And you should get something very close to 1 psi per foot. Okay, so let me see. Let's go to point number 8. The same as a vertical stress gradient, also we have a pore pressure gradient. And if you want to calculate this one, it's going to be, again, this number over here, minus that number over there, divided the depth. That's going to give you the pore pressure gradient. A typical pore pressure gradient in hydrostatic condition is 44 psi per foot. But probably that's not going to be what you're going to see in this case, because in this particular place, there's not the hydrostatic gradient. Okay? So I'd like that you tell me what that value is. The vertical stress gradient, I told you how to calculate it, so you should know how to do that now. If you know the stress gradient from B, and you assume that that's constant everywhere in this particular place, you should guess it's not going to be a perfect value because you're doing an assumption, but you're going to have an idea about the depth at this location A, which in this case, I mean right there, at this depth.
So what are you asking? You're asking the depth of A?
Yeah, I want to know here, the guys that wrote the paper, they don't want to tell us what is the depth.
Okay.
Because they don't want to reveal that information
Okay.
to their competitors.
Okay.
So what we're going to do is using these values over here, we're going to guess more or less what is the depth.
Okay.
Okay?
Yeah.
Okay. The next point is going to be to write these stress tensors for locations A, B, C, and D, and E, like a matrix like this one at locations A, B, C, D, and E. Something very interesting in this case is that sometimes you have the minimum principal stress to be horizontal, like for example in this region, but at some particular places here it is not, and it changes, and now the vertical stress is the minimum stress. That's going to be very important when we talk about hydraulic fracture. Okay, so keep an eye on that. And also here it looks like the minimum horizontal stress is increasing and it's getting larger than the vertical stress. All right, so we know how to do that. Now let's talk about this point.
So quick question on question D. So are we still assuming that the vertical stress is the principal stress?
Yes, we're going to assume that vertical stress is principal stress. So there's not going to be shear
That's
in the
okay.
in the compound, in the off-diagonal term. Okay, So we were saying before that there are places in which the horizontal stress may be the minimum principal stress, but there are some other places like over here where it is not. So those variations are very important, and there is a classification for that to tell how those may be ordered in a particular place. So in a place where the maximum principal stress is S1 larger than the intermediate stress and larger than the minimum principal stress, we're going to say that a given place is going to be under a normal stress regime. Let me save some words. I'm going to put stress regime over here. It's going to be normal whenever the maximum principal stress is vertical and the other two are horizontal. Of course, SH max is going to be always bigger than SH min. And this is the case, for example, at depth C. Let's go to depth D. In depth D, this place is called reverse, and the maximum principal stress is horizontal. The minimum principal stress is vertical, and the intermediate principal stress is horizontal. And that's the case like that one. And there's going to be a third one, which is called strike slip. And in that case, the maximum is horizontal, the intermediate is vertical, and the minimum principal stress is horizontal. The name from these three types of stress regimes, it comes from fault analysis and how faults slide with respect to each other. We're going to talk a little bit more about that next week. But for example, in a place with a normal stress regime, you're going to have normal faults. In a normal fault, usually if you have a formation somewhere over here, it slides in such a way that this one goes down, this one goes up, and of course here, this is SV, and this one is SH min. We're going to see later on that this is a type of shear failure. Okay, I'm not going to get into that right now, but this is what it's called. It's a normal fault. The hanging wall goes down over the footwall. Don't worry about this terminology, okay? I just want to make this description complete. This is called reverse because it happens the opposite to what you will have in a normal condition. And in this case, if you have a formation somewhere over here, the horizontal stress is going to be so large that it's going to overcome the vertical stress and it's going to produce a fault with hanging block to move over and to move up with respect to the footwall. Notice that in the first case, SV is kind of pushing down. Let me make a So the animation, please. This is lower. So SV is moving down this block against SH mean. In the reverse case, SH max is bigger, is pushing the block against SV, but SH max is bigger, so that's why it leaves the hanging wall. And the third type, it is called strike slip, because when you look from the top, it's going to be a difficult drawing. I'm going to try anyways. Now this is a 3D drawing, okay? This is a block. We're going to have a vertical fault, and the slide is going to be along the strike of the fault. And in this case, I'm assuming that SH max is coming in this direction. And SH mean is in this direction. And because the fault just moves along the strike of the fault, which is this line, that's why it's called strike slip. Okay, this is going to be super important. Yes?
Talking about the normal stress regime, you're drawing a sign that is saying that the SH mean is always compressive. Is
Yes.
there a possibility that in any setting to have this as a tensile stress also, or?
It's very unlikely. It's going to be most times always compressive, because the weight of the rocks made rocks expand in the lateral direction, either because of the Poisson effect, or either because they fail in shear, and because of that, there is going to be always a compression. Probably if you go to a place in which